In this lecture, we're going to look at the modeling of an analog to digital converter and a digital to analog converter. Because the processes that we control are analog in nature, whilst the controllers are digital in nature, we need an ADC and a DAC. An ADC is used to change the input error signal into a discrete form that is suitable as input to the algorithm. So the algorithm works out the control signal and it gives it out in digital form. So a digital to analog converter will be required to change the discrete control signal into a continuous control signal that is going to be input into the process so as to control it. Let us look at the modeling of an ADC. We also refer to it as sampling. For a given continuous function ft, the task of an ADC is to pick off a sequence of values fkt for k equals 0, 1, 2, 3, etc. The input to the ADC is continuous, whilst the output is discrete. The input is denoted as ft and the output is denoted as f star t. The ADC essentially consists of two components. There is an ideal sampler to pick off the current value of the continuous function. Then there is a large register that is used to store the sampled value until the next sample is picked off from ft. The sampler is modeled as a sequence of impulse functions. The functions are at instance 0, t, 2t, 3t, 4t, etc. The mathematical expression for the sampler is a summation of these impulse functions. In compact, it is represented as summation for k equals 0 to infinity of delta t minus kt. Suppose we've got this continuous function ft that we want to change into a discrete signal. So to change it into a discrete signal, we impose the sampler on the function ft. This is essentially multiplying the function ft by the sampler function. So as a result, the output of that process is a signal defined by the summation for k equals 0 to infinity of fkt by delta k minus kt. And this is the diagram showing the output of the conversion. It is a sequence made up of the values f0, ft, f2t, f3t, f4t, etc. If we take the Laplace transform for the ADC output, we will find that it is given by the expression summation for k equals to 0 to infinity of fkt by e to the minus kts. If we define z as being equal to e to the ts and substitute into the Laplace expression, we will find an expression that is equivalent to the z transform of the ADC output. Therefore, an ADC is modeled as an ideal sampler represented using the z transform, where the z transform is defined as the Laplace transform of the sampled output taken with the z defined as being equal to e to the ts. Z is a unit advance operator, meaning that it advances by one sample period. Correspondingly, z to the minus 1 is a unit delay operator, meaning that it delays by one sample period. Sampling is essentially mapping of the S-plane into the Z-plane, and we define Z as being equal to e to the ts. We know that S is a complex number made up of an imaginary and a real part, and is expressed as S equals sigma plus j omega. So if we make substitutions into the definition for Z, we find that Z is equal to e to the sigma t by e to the j omega t. From there, we see that the magnitude of Z is given as e to the sigma t, and the argument is given as being equal to omega t radians. If we make S to be the subject of the formula, in the formula Z equals e to the ts, we find that the real part sigma is equal to ln of the magnitude of Z over t, and the imaginary part omega is equal to argument of Z over t. We have an example where we want to obtain the mapping of the point S equals minus 1 plus j in the Z plane. We are given t as being equal to 1. We notice that the real part is minus 1 and the imaginary part is 1. Using the formula, the magnitude of Z is equal to e to the minus 1, which is 0.368. The argument is equal to the real part by t, so it's 1 by 1, which is 1 radian, or 57 degrees. From the definition of mapping and from the fact that S is a complex number, we can express Z as a product of two exponential terms. The first term is an exponent being a real number. The second term is an exponent being an imaginary number. We will notice that we can add multiples of 2 pi to the imaginary exponent without changing the value of Z. Now, different multiples will correspond to different points in the S-plane. Therefore, a single point in the Z-plane will correspond to many points in the S-plane. Sampling frequency is given by 2 pi over t, where t is the sampling period. So as an expression, all points in this S-plane that satisfy the expression S equals sigma plus or minus j, open bracket, omega plus n omega s, close bracket, where n is a whole number, will map into the same point in the Z-plane. We call it many-to-one mapping. The diagram illustrates the mapping of points from the S-plane into the Z-plane. The S-plane can be divided into a number of horizontal strips. From each strip, only one point will map into a given point in the Z-plane. This means that the different points that map into a single point in the Z-plane come from different strips. The strips can be described as primary strip or complementary strips. In the primary strip, the points have n being equal to 0. In other words, the multiple of 2 pi is 0. In the first complementary strip, which is a strip above the primary strip, the value of n is 1, meaning that the multiple of 2 pi is 1. In the second complementary strip, the value of n is 2, meaning that the multiple of 2 pi is 2. So we have described going in the positive direction above the real axis. We can apply the same argument for strips going in the negative direction or below the real axis. So for points below the real axis, the value of n will be negative. Let's look at the mapping of points from the primary strip into the z-plane. Points on the imaginary axis in the s-plane, you have a real part being equal to 0. Correspondingly, the magnitude of z is going to be equal to 1. Therefore, points that are on the imaginary axis in the s-plane will map into a circle of unit radius in the z-plane. This circle is called a unit circle. Points that are in the left-hand plane of the s-plane, you have a negative real part. In other words, the real part is less than 0. Correspondingly, the magnitude of z is less than 1. Therefore, points that are in the left-hand plane will map into the interior of the unit circle. So points in the interior of the unit circle, you have a magnitude of less than 1. Points in the right-hand plane of the s-plane, you have got a positive real part. In other words, the real part is more than 0. Correspondingly, the magnitude of z is more than 1. Therefore, points that are in the right-hand plane of the s-plane will map into the exterior of the unity circle. Aliasing is when samples represent more than one frequency. As an example, using the diagram shown, we have 3 samples and 2 frequencies. The 3 samples belong to both the frequencies. So given those 3 samples, it is difficult to tell which of the 2 signals is being represented. So aliasing will make it a challenge to differentiate between frequencies when there's need to do so. So this means we need to employ some measures to avoid aliasing. The first measure is to sample at a frequency that is at least twice the highest frequency component in the signal. We refer to it as the Nyquist sampling theorem. The theorem technically excludes the possibility of aliased signals in our system. The second measure is to filter the signal before sampling so that it meets the requirements of the sampling theorem. Quantization errors are errors introduced due to digitization of continuous signals. The magnitude of the error is related to the resolution of the ADC and therefore can be reduced by improving the resolution. We note that sensors have got a limit on accuracy. So as we improve the resolution of the ADC, we make sure that we don't increase it to beyond the accuracy of the sensor, as that move will be not worth it. Another thing to note is that the ADC conversion time is selected to be negligible as compared to the sampling period. Let us now look at the modeling of a DAC. We also call it extrapolation. The simplest form of a DAC is a latch register. The latch register is updated with the control value once every t seconds. Once a control value is written to the latch register, it is held in there until the next update. If you look at the diagram, we see that at t equals to 0, the value U0 is written into the latch register, and that value is maintained until time t. At time t, a new value ut is written to the latch register. That value is maintained until 2t. At 2t, another value u2t is written to the latch register. It is maintained in there until 3t. So this happens continuously as long as the DAC is running. The ZOH is modeled as writing and removal of step functions. Looking at the diagram, at time 0, we write a step of magnitude U0 to the ZOH. At time t, we write a negative step of magnitude U0 to the ZOH. This has the effect of removing the portion of the first step that starts at t and ends at infinity. Effectively, we remain with a rectangular pulse of magnitude U0 between time 0 and t. At that same time, we write a step of magnitude ut to the ZOH. At time 2t, we write a negative step of magnitude ut to the ZOH in a manner similar to the first one, so that we generate the second pulse of magnitude ut. We repeat the process continuously. Mathematically, the output of the DAC can be modeled as a summation of positive and negative delayed step functions. In our expression, the first term is responsible for generating the first pulse. U0 is the magnitude of the pulse. LT is a unit step function that starts at 0. LT minus t is a negative step function that starts at t. In the second term, ut is the magnitude of the pulse. LT minus t is a positive step that starts at t. LT minus 2t is a negative step that starts at 2t. The argument applies to the rest of the terms in a similar way. Let's take the Laplace transform of the DAC. Using some mathematical manipulations, we can factor out the term 1 minus e to the minus ts over s, so that our Laplace transform is a product of two terms. The second term is recognized to be a Laplace transform of a sequence made up of the values u0, ut, u2t, u3t, etc. We also realize that the sequence is the input to the DAC. Therefore, the second term is the Laplace transform of the input to the DAC. The Laplace transform of the input to the DAC is represented as U star S. So if we make substitutions, it means US equals 1 minus e to the minus ts over s times U star S. We can then manipulate this expression so that we obtain the TF of the ZOH. The TF is equal to US over U star S, and it works out as 1 minus e to the minus ts over s. We can represent this using a diagram. So we obtain a sequence from the algorithm. That sequence is expressed as UK. Its Laplace transform is U star S. The sequence is input into the ZOH. So the ZOH manipulates this to give as output a continuous signal UT. The Laplace transform of the output signal is US. S. Try out these questions from chapter 6 as exercise.